Hello, good afternoon. I was just going to say thanks for the introduction. I didn't understand a word, but I hope it was nice what he said about me. My name is Marion. I will be speaking about rogue behavior detection. This project deals with malicious binaries and opportunities in static analysis that help the reverse engineer. The idea of the project actually came up due to my hatred of sandboxes, because I was told to use sandboxes on binaries where the sandbox wouldn't help me anything. So I put all my anger into this project, and I hope you enjoy the presentation. As I was just introduced, my name is Marion. I'm a malware analyst working for GData Advanced Analytics in Germany. And today I'll be speaking about my project in analyzing behavior of binaries statically without actually executing the binary with the help of RedRE 2 and graphs. All right, let me start. Malware analysts are special creatures. We have a lot of issues. Our main issues are we're lazy, we hate repetitive work, and we're pretty expensive. That's mainly a problem of our employers, but they sure as hell want to help us in our work and want to aid automation in our work, because human analysts are usually not the best option to do binary analysis in the first place. On the other side, we have a lot of issues with the automation of malware analysis as well. The analysis itself is usually a very exhausting task to reverse engineer an entire binary, but on the other side, the binaries themselves are not that sophisticated, not that interesting. There is a lot of media fuss about the challenges of malware in general, but I'm telling you, they're not always true. So in malware binaries, you find a lot of repetitive code. You find a lot of badly written code, because malware authors aren't usually professionally taught software developers, but they are people who are frequently self-taught. This is how the code usually looks like. Also, malware frequently has limited interests. Like there's a limited set of functionalities that you will find in 90% of all the malicious binaries. Malware might try to steal key strokes. Malware might try to download other binaries from the internet and execute them. Malware might try to search the file system for interesting documents. Malware very seldomly uses, for example, GUI or graphical applications. And there's a lot of other things that malware frequently does not do. So we have rather simple binaries that aim to make it very difficult to be analyzed. So given this situation, having boring binaries, having lazy and expensive analysts, and having limited interests, it would be very neat to have tools that just analyze the binary for you and show you at one glance what the malicious software is intended to do. But that gives us a set of problems. Automated malware analysis is still an unsolved problem that people nowadays usually tackle with sandboxes, with dynamic analysis for executing the binary and gathering forensic information from the sandbox system itself. On the other hand, we have the static side that for automation is frequently not feasible for a couple of reasons. Actually, there is a lot more reasons than listed here, but summarizing them, we usually have to deal with runtime packers, with code obfuscation that make the code unreadable at first glance. We have self-modifying code which changes its behavior or its structure at runtime. We have virtual machines that parse bytecode, which is usually not that easy to analyze statically or very cost-intensive. We have dynamic API loading, which hides the APIs the malicious binary would use and hides its functionality from a static perspective. We have asynchronous code, which statically is usually difficult to put in context without executing the binary. And we have object-oriented code, which by its nature is hard to analyze. But I do personally think that these are challenges that we can overcome and analyze or aid with dynamic analysis, and primarily should focus on the static analysis of malicious binaries. Because on the dynamic side, we have just nearly as many issues to overcome, and a lot of them are actually, in my belief, very much more difficult to solve. First of all, of course, we have sandbox detection, which is something that sandbox developers primarily focus on, but what they usually still nowadays are not able to overcome is, for example, missing dependencies. If you have a binary which depends on a second binary or maybe a whole framework of binaries around there, the sandbox will not be able to analyze that binary because the rest of the dependencies are just missing. This is very common with nowadays malware, where plugin systems and frameworks are frequently seen, and an antivirus company or a sandbox company might just have like one little piece of the bigger puzzle and is not able to analyze it. This is frequently seen with DLS, for example, that might even be able to run in a standalone context, but due to their structure, it is hard to find this one dedicated execution path or this one dedicated export that would actually trigger the malicious functionality. Also, some binaries show a need for interaction, user interaction or interaction with the remote server. For example, if you put a binary into a sandbox, which first of all its actions wants to get input from the remote server, which might be offline or might not be reachable from the sandbox, the malicious binary might decide not to execute and show its full potential. Also, we have time-based evasion and missing input values and incompatibilities. But what I personally think is the biggest problem that we have with modern sandboxes, which I haven't seen solved in the past, is multiple execution paths. Usually, a simple malware binary will potentially show you its whole functionality because there's one single execution path from beginning to end. If you, for example, take a malicious downloader and put it in the sandbox, it will execute from beginning to end and then download the second stage malware, and you've seen everything this binary can do. This could look like the following graphic. So, for example, we have the malicious binary, which first unpacks itself and shows its evasion and tries to detect the sandbox or however it is protected. Then after that stage, it starts its setup. Then after that stage, it might call its remote server, download further binaries, and then things go sideways. So this is usually the modern problem of sandboxes, that the first three stages of this process, however they're structured, are easy to simulate. Then the last stage, where the final functionality should be triggered, is very hard to simulate. If you think, for example, about a common RAT, a common remote access Trojan, you see the first three stages, and then the Trojan expects input from its remote server. It expects the controller of the bot to send commands to be parsed and to actually trigger functionality. This is very difficult for sandboxes to analyze, because sandboxes usually are not that smart to determine which different paths the malware can take. So all you see there in the sandbox is then the Trojan waiting for input. And sandboxes, just like most other analysis systems, have time constraint, which means you can't just wait for 2 weeks until the bot operator decided to send all the possible commands to your Trojan. On the other hand, this is especially true for benign binaries. Like, while on malicious binaries, you might still have programs that just execute from beginning to end and show everything they can do. Benign binaries just never do this. There's very little benign binaries that actually do not require user interaction, like someone clicking in a GUI or writing text or clicking the save button or interacting with the application, because that's usually what programs are written to do, especially on modern desktop operating systems. So this is a point where sandboxes, in most cases, actually fail completely. On the other hand, also many sandboxes today rely on API hooking, which technically means someone monitors all potentially interesting APIs that an application can show. This is usually limited because this is cost intensive, and usually sandboxes see to only hook into interesting APIs that they consider potentially malicious. But for example, user interface, the user interface or general user interaction APIs are not considered interesting. The sandbox actually miss this context completely. Okay, so here would be the need for my wicked plan. What I actually tried to do with my project was look at all areas of a binary. And as simple as it sounds, this is something that very little analysis systems nowadays manage to do. If you do a purely static approach, you might be hindered by packed and obfuscated binaries. If you do a purely dynamic approach, you might be hindered by the problem of multiple execution paths, and that you can't just see everything that the malicious software was capable to do. So I came up with an idea, which right now I admit, is still limited by these constraints, but in the future should potentially help analysis systems to improve on their capabilities. So I wrote a tool which helps me look at API calls, strings, and the general structure of a binary to find out more about its intentions, or potentially also determine whether it is packed or a binary that tries to hide its functionality, which is something I consider suspicious. I did this with the use of graphs and the use of RedRE 2. RedRE 2 is a disassembly framework. I'm going to be explaining a bit more about that later, and graphs are an interesting data structure that is very helpful in terms of determining context. And interestingly, when I say graphs, a lot of people think about something like this. So now I did not paint graphs with Microsoft Excel, but I was actually talking about real graph structures. Graphs are interesting in binary analysis because binaries naturally are graphs. A binary has, for example, what I used, the function call graph. So one function calls another function, calls another function, calls 5 other functions, and so on and so forth. So binaries are naturally structured like graphs, and graphs of graphs, because within the function you have the control flow graph, the CFG, with basic blocks, where one basic block refers to another basic block, and so on and so forth. So you see the binaries actually are perfectly suited for analysis with graph structures. Also, graphs are pretty great for visualization. As you can see on the screen there, that's a graph visualization, which in its current context isn't very helpful, but I thought it's super pretty. Also, graphs are really interesting data structures from a mathematical point of view, but let me say that from the beginning I'm not a mathematician, so don't expect big formulas, but I might have some numbers to show in the end. So yeah, I use these graphs that you can extract from binaries and try to fit them with strings and APIs that would find within binaries. And now again, why does this make sense? At least in my head, it would make sense for the following reason. So earlier this year, I worked on a project with a colleague of mine who works in incident response on a set, or a larger set of targeted binaries. And within that set, we found that most of these targeted binaries, or that are being used in the context of targeted attacks, are not actually packed or obfuscated. This is something that incident responders have known for a long time now, which we tried to prove with actual statistics. And if you look at that slide, there's 3 groups of samples being described. There's on top a set of benign binaries. The total number of that benign set, so like, yeah, the numbers are hard to read even for me. The total numbers of all 3 sets were about 6,000 to 7,000. I limited the sets to make them comparable. And the benign binaries on there stem from real applications, like from Firefox or from Microsoft Word, and so on and so forth. Someone in my company has a hobby and collects like all the benign binaries for signatures to test, and I just grabbed their binaries from them. On the other side, we have the targeted set that we collected, and then we used a randomly chosen set from the malware from a malware repository, where this was like really random. My solution for picking random malware sets from big sets is to sort them by file hash. Then this is the only attribute that you can gather from a malicious binary that really assures you that you have a random set. Lots of people just go to VirusTotal and download the latest uploads, and then they wonder why they have like 2 different kinds of malware in there. That's not the right approach to go. For packet detection, we used a sort of attributes that I listed on the screen that might or might not be real indicators for packers. I found them useful, but one would have to try it himself. My proof for that in the end was that we got the following statistics that are listed there. These screenshots might not look that different at first, but one has to consider the numbering on the side, which actually for the random set, the numbers are a lot lower than for the, should be lower than for the benign, the targeted set, which means that on the far left side of the statistics, you have the 0 column, where there's 0 indicators found, and for the histogram part on the right side, there's indicators being found. So within the benign set, you have this big bar on the left. For the targeted set, you have this big bar. And for the random set, the bar is a lot lower with 0 indicators. And the other bars with indicators are a lot higher. Actually, these 2 outliers that you can see in the benign and the targeted set, I don't know if you can, like especially for benign, you see 2 bars that are higher. That's UPX in different combinations. I check that. So you can see that benign is usually not that packed. Targeted is sometimes a little bit packed, and the random set shows a lot more indicators for actual packers. That's just numbers. We we looked into the binaries themselves and found that the numbers are pretty accurate. So that's why I started the tool. But why did I actually want to write the tool? About that graphic, try to go to Google and search for a useful picture about the word why, and this is the first thing that pops up if you search for it. And I like the toilet a lot. So why did I try that? So I wanted to have a tool which helps me in static analysis for small to medium size sample sets. What I wanted was like a tool that helps me look at 5 to 20 to maybe 50 samples and help me gather at one shot information whether they're packed or they're not packed, or they look suspicious and try to hide APIs and try to hide strings, or whether they actually look like totally normal, whether they contain APIs that are used for GUI applications or for graphical purposes. And this is why I started to write the tool. The tool that I created is supposed to be easy to handle and extendable. I still have to work on the code a bit more, but it's only 4 sets of Python scripts that interact with RedRE 2. I'll be talking more about the tool later. So yeah, I have the tool and try to extract metrics and behavior indicators. But what did I actually not try to do? So I've been talking a lot with people about this presentation before, and they were like all about data analysis and big data and automation and big data and the bigger data. And I actually didn't try to collect a lot of data. So I tried to focus on get accurate graphs and get the visualization and the output data in a correct way, and did not intend to do clustering. The data that I extract and some of the features can be used for clustering. If someone is interested in that, I'm happy to share all my data, but that was not my goal. Also, I didn't try to do binary diffing. I know graphs have been used for diffing before, and that's surely a good thing to do. But as it is not that easy with a usual notebook to do large-scale diffing, I didn't make that my primary goal. And for sure, I did not want to do machine learning. I found a very nice quote on machine learning recently on Twitter, which says, I need a ball-labeled ML so I can throw machine learning at things. I'm really not the biggest fan of machine learning with binaries itself, because I do believe that for proper machine learning, one needs a reliable set of features. And if there's one thing that malicious binaries usually do not want to give away, it's reliable features. So it is very hard to create a large feature set for a large group of binaries that is not like inconsistent in one or another way. All right, so what did I do? I painted graphs. You can maybe see the lines between these blobs. I cannot here. But this is a graph that my tool has output, and one of the prettier graphs because it's nice and structured and it's actually small. What you can see there is a rat, a vector Trojan, which gathers information about the infected machine and gathers information about the user on there and connects to a remote server and downloads a binary and can execute binaries. It's just a very simple piece of malware. What you can see there are the blue nodes are the exports. So this is a DLL, the marked exports in blue, and the green nodes are callback functions or handler functions, for example, for create thread or for hooking functions. And all the pink nodes are normal function graphs, function nodes. So the nodes always comply with a function within the binary. The edges are function calls among the local functions within the code section of the binary. And also, what's not visible there is white nodes. White nodes are functions that do not show any API call or any string. So it's just colored nodes that contain actual content. Okay, how did I do this? I used RedRE 2. You wouldn't believe how much ditching you get in the RE community for not using IDA Pro, basically. I chose RedRE 2. It's a disassembly framework that's based on the command line. It's best to run on Linux, although there is a version that runs on Windows too. It can be scripted from Python, which is very nice. The feature set of RedRE 2 is very big. You can disassemble all sorts of platforms with it and disassemble all sorts of binaries as much as you want and then look at the code on the command line, which is, I think, what keeps most people from using it. What keeps most researchers from using it is that there's still a lot of bugs in there that are being continuously fixed, and there's being new bugs produced every day, I think, as well. But what I found is that the RedRE team is actually very helpful and willing to fix all the bugs in their tool, which is not the case with IDA Pro. Anyway, so that's not actually the reasons why I use RedRE. Yeah, a little bit more about my use of RedRE soon, but the RedRE is actually pretty nice. So yesterday, I talked to the RedRE developer, and he was like, no, stop telling me about graphs. I improved the user interface. We now have like a continuous pixel line in the visual mode. So you have a visual mode, and they fix stuff on that all the time. And they also implemented modules to disassemble all sorts of machinery with Tamagotchis and processors on the Apollo 11 platform and whatnot. So this is still cool, but what's my reason why I use RedRE? So I chose to use RedRE because I have so much fun working with these crazy disassembler people, and because it's scalable. So RedRE is open source, it's free, you can download it, you can deploy it on one machine, you can deploy it on 200 machines, it doesn't matter. It's questionable whether it runs continuously there, but you can use it, and that is cool. You can script it, which I did using Python. It's GUI free, so when you automate it and script it, you don't have the IDA Pro GUI popping up and down all the time, which get me kind of nervous every time I scripted IDA Pro. And you have great support, so people are really interested in having others use their tool and actually are interested in helping them to get their head around RedRE. And finally, what did I need from RedRE? So RedRE, like IDA Pro, has the capability of analyzing entire binaries and detecting functions in there. And what I wanted were the functions and their cross-references. So I wanted the function, which calls another function, to have my edges. I wanted the cross-references on symbols that were referenced within the functions and the cross-references on strings. So this is the data that I consider most useful in the analysis, in the quick analysis process of a binary. It also gives me basic P information that I can fit into my graphs to make them more, to make identification of the graphs better. And also a cool feature, every time you start RedRE, you get the quote of the day, which is usually not very serious. And what I found is that you can also pump RedRE through the lolcat script on Linux and get rainbow-colored disassembly. I was super happy, and I really liked to work on that disassembly. Anyway, so back to RedRE. Running RedRE in a scripted way is fairly simple. You have modules, for example, for Python, you can download the RedRE module and then just get a handle on a RedRE process that's started by your Python script, which means you open up your input file with R2 pipe, and this gives you a handle to pump commands to your RedRE process. You do not have to deal with C, which I can do, but I prefer Python actually, and then you can just execute commands. The commands are, I admit, one of the bigger issues of RedRE because they're really not easy to understand. So I listed all of the RedRE commands I used on that slide. If someone wants to get his head around RedRE, here's a little help. I will not go into details about these commands right now. At this point, I also want to say thanks to the RedRE development team because they wrote half my tool by feeding me all of these commands, basically in their Telegram channel. Usually, when you start on RedRE, you post your question there, and someone sends you back command lines. And then you just use these command lines. That was my way to learn RedRE. Okay, how does the tool look like? So I did not only rely on RedRE and R2 pipe, but also used NetworkX to create the graphs. So I got all the functions and their cross-references out of RedRE and piped the data on into NetworkX, which is fairly simple. It's 5-6 lines in Python to just create a graph. You have to create all the nodes, and then you add all the edges, and then you have a graph structure. It's super simple. Also, the plotting turned out to be super simple. If you refer to PyPlot, there is a lot of libraries that help you plot NetworkX graphs, but PyPlot is the one that's easiest to access, and actually the one that helps you even get node data into the nodes. What was my problem with graph structures in Python is that that's usually used by mathematicians, and mathematicians like nodes and edges, but they do not really like data within their nodes. What was interesting for me was data within the nodes. So I wanted the API calls and strings, and I actually also wanted to visualize them. That's something that's fairly difficult to arrange with NetworkX. The solution for that is to use PyPlot and assign the strings and what you want to see within the nodes as labels to the actual node. Then you can read what your node actually contains, which is a bit of a workaround, but it works more or less. For static PE file information, I didn't use RedRE, I used PE file, which is written by Eero Carrera, who's also a guy who contributed to most of my projects without knowing about it. And I'm very grateful about his work. And Neo4j is currently my solution for a backend. Neo4j is a graph database. You can just port your graph into the database, and then you have the graph structure there. You can also do a lot more magic with graph databases, but I also didn't go all the way there. It's still space for a future project. I'm actually working with that graph database. Because in theory, you can represent a set of binaries within the graph database, and then see whether you can find links in there. I'll be talking a bit more about that in the end of the talk. The project will be published soon, or actually there is also already code on my GitHub profile if you want to check it out, but I warn you, that's still proof of concept. I went the usual software developer way with that project. I did not really design anything, but just stack functionality on top of each other. So there might be some bugs in there, and it might not work with all binaries, but it's already public. Okay. What did I do? A binary art project. You saw the graphs before. You saw that most of the graph is pink. That's not because I like pink so much, but actually because I like to annoy people. That's why I paint things pink. But we're going to see a lot more pink graphs soon. How did the graph generation work? As I mentioned, I used functions as my nodes and function calls as my edges. But that's not all that simple as it sounds like, because there's a lot of calls of different types within a binary. And all that I was interested in for the graph generation were local calls from functions within the code section, but not actually calls to APIs and so on and so forth. Also, with most binaries, you have the problem of indirect calls. Especially in C++, you find a lot of calls that go to member functions, which actually call into some offset within some object, which statically is very hard to parse. It's also still open for a future project, so I didn't primarily deal with C++ binaries because of all the indirect calls that I cannot resolve. Within the graphs, I identified 3 different kinds of calls, or 3 different kinds of cross-references, which of course were references to other functions, which were the component of the graph. But there's also references to code that do not refer to a specific function. This is something that primarily happens with packed binaries. So when RedRE is not able to detect all the functions, it will show you calls that go somewhere in the code but do not refer to a function. This is also implicit an indicator for whether the function parsing worked or not. And funny enough, throughout my project, I saw a lot of improvement on this parameter. So in the beginning, when I ran the parser, I saw a lot of references that were going to nowhere. And in the end, after I submitted all my bugs, I saw a lot of calls that all of a sudden found a function. That was super funny to watch. Also, occasionally, you find calls that go outside the executable section, which is something very curious, because I found out that's usually when the function call refers to a global variable, which is located outside of the executable section. And this, for me, is an indicator for dynamic API loading. This is not always the case that dynamically loaded APIs are stored in global variables, but this is something I saw in the past with lots of, especially targeted malware. That's for me an indicator that, as mentioned, APIs are loaded dynamically. So right, the nodes are functions, the edges are calls, and also handler functions. So in a limited approach, I tried to identify callbacks or handler functions, especially for create thread and for Windows hooking, to be able to identify whether some special node that didn't have any references would be used as a thread function by create thread. I'll be talking about that soon. Yeah, and here again, an example for a very small and very pretty graph. Strings. So the first thing that I personally try to find in a binary that I want to analyze is strings. Why? Because they're super easy to find, they're super easy to parse, and usually you have a lot of information, also information that's possibly contextualized. So it's something that the human mind can read and understand. But there's a couple of issues in collecting all the strings. So string parsing in RedRE works the way that either the code section or the entire binary is searched for something that looks like a string, and afterwards you still have to parse for ASCII compatible strings, which reduces the fun string set considerably. And then, as mentioned before, there's cross-references stored for strings. So you just have to find the cross-reference of a string within a function, and then you can create the link between strings and their respective functions. Yeah, on the slide you can see the string listing from a common ret, from RedHip, I forgot the name. I'll be also talking about that ret a little bit later. But this is a wonderful example of how targeted malware just shows all of its string content in clear text, if you just analyze it. One might wonder, so a common question that I have to deal with, why is this happening? Malicious software, so security software is frequently based on an ecosystem, or their intelligence is based on an ecosystem. So when something malicious is found a lot of times, it is added pretty surely to the databases of antivirus vendors. But this system only applies to, as I call it, mass malware or software or malware that's used in different contexts. If you have targeted malware, which is used in very little contexts and usually on targets with different antivirus engines, they have very little chance to actually catch these binaries. So it's unlikely that someone will create a signature for these binaries, although it would be super simple to create a signature for example, the commands that are listed within the binaries. I also implemented a string list detection, because I found very frequently that functions would work with lists of strings that were seen in the binary as a continuous list of addresses. But in the graph I had the problem that I would only see the first item. So cross-reference always links to memory, to an address, and you can link that address to a graph. But if it's like an offset for a list, you will miss the rest of the strings that comes afterwards. So I tried to parse these lists and now fit lists into graph nodes, which occasionally makes the nodes very large, like very long. And then you have the strings in there. Yeah, and what's the information one can gain from strings? As you can see, you can read them, you can think about them, and you can come to a conclusion. But there's also more information you can get out of there. You can see, for example, that one string is used in a lot of different nodes. You can see that one string that's very long is potentially not used in any node. You can see that these strings have a certain language. So for example, English or not English or Chinese or whatever. And sometimes you can even gather bugs from strings. So it has happened in the past that I saw strings within binaries that were written the wrong way. And this is something rather curious, because if you copy-paste code, you might also paste strings. If you copy-paste code within your different applications, within your different trojans, you're very likely to not fix the bugs or the mistakes within the strings. And this is something very indicative for continuous use of code. Someone might copy from Stack Overflow, or might copy from repositories, but the usage of wrong language within binaries is usually something that one doesn't do twice. If someone makes a typo or a mistake within a string, he doesn't always do that. He usually makes these mistakes in different forms. So typos within strings help you to actually link code repositories or reused code within binaries a lot better than normal strings. On the other side, the APIs. I'm not sure you can read that. I don't think so. Anyway, that's a list of symbols that RedRE parsed out of one of the binaries. So you can see here on the right side, for example, the name of the DLLs or the libraries that contain the symbol and the actual symbol name. For my project, I only used the symbol name, but I planned in the future to also use the library name to try gather statistics about libraries that are being used within binaries and the actual symbols being referenced, like how much usage I can find of a specific library, and so on and so forth. But here, on the right side, you can see the addresses that are used for putting these cross-references into context with nodes. A problem here, as mentioned before, are indirect calls. Thankfully, RedRE finds symbols also when they're used as a data reference, when they're, for example, loaded into a register to be used later on. And I still had to go on and follow these registers within the functions to find references to the specific symbols that I was searching for. That wasn't all that simple. In the end, what I also did was thunk pruning, which refers to thunks that are frequently generated by compilers, which I do admit is something that IDA Pro is fairly good in doing. So if you open a binary within IDA Pro, you will see marked references to imported symbols, which are actually thunks, which in the disassembly you can see as very small functions that have nothing but a jump to a specific import. And this is something that RedRE didn't do itself. But it was also a very interesting project to fix these thunks, and I would recommend you looking into compilers. It is a very interesting topic on how thunks get into binaries and how they're used from compiled binaries. And also, as mentioned before, dynamic loading is a problem. This is something I haven't even nearly fixed now. That when APIs are loaded dynamically, you usually see a call to get proc address, or maybe not even that. And afterwards, the offset of the API that's loaded dynamically is stored within the binary and can be referenced multiple times. So for example, you could dynamically load your crypto API functions and then use them within the binary, and I would not automatically be able to follow these calls. But I'm still working on that because, as you saw before, there's lots of strings within binaries, and if I can manage to find strings being used within the get proc address calls within the binary, I might be able to link the output of these APIs later on, either to global variables or to memory structures that I can possibly link to function nodes. So this is something I'm still working on. As mentioned before, callbacks and handler functions. That's a problem that I started to deal with already. There's two approaches to find handler functions. I primarily did this for create thread and set Windows Hook X, because that's the functions that interest me most in the context of malware. And there I just check whether I can find a push instruction before these APIs that references to a function. This is a little bit tricky to get the actual APIs for specific functions. My luck there is that most Windows APIs follow the same calling declaration, so it's rather easy to find the push instructions, but the problem in finding all the arguments being used within one specific API is that there could be function calls right in between the pushing operations. As you see fairly often, if, for example, a window handle to the current process or something similar is used by the final API, that you see the function call to the API that retrieves that handle within the push operations before your API. So given the problem, I cannot just get all the parameters, but went away to search for push instructions with function references. That's a little bit of a workaround. On the other side, what I tried was searching for nodes within my graphs that didn't have any incoming connection, like any incoming edge, and consider these nodes handler functions or offsets that are being dealt with in different parts of the binaries. And then I just went to search for cross-references, like bottom-up, from the node up, to see whether these offsets were referenced within the binary. And then could add this to my graph. This is all a bit of an approximation to actually get these nodes. This is certainly not the most complete technique to find, to fit callbacks or handler functions into my graph. But for the purpose that I did, or for the tests that I ran, it worked considerably well. And the last problem that I wanted to talk about, or actually not a problem, but a kind of a feature, is that compiler settings and optimizer magic within binaries is something that does not really affect my work. So with the graphs that I created, I followed the objective that I did not want much data. I wanted like small data. I wanted to collect as little data as possible with as much information as possible. That's why I only picked APIs and strings as the objects to extract, because these, for me, contain a lot of information, are easy to extract, and are little data to store. And then I mentioned that problem to a friend of mine who's a developer, and he was so friendly to create some binaries for me. So we used an example code from MSDN and compiled it in different ways, and here is the output. from the graph analysis tool. So sadly enough, he sent the binaries to me and gave them specific names, but I have absolutely no idea what the exact settings of his compilers were. So one was tag default, which I guess is just when you do nothing on the most modern Visual Studio version. This is the top left graphic. And the others are either fully optimized, size optimized, or created with different versions of Visual Studio. The one from 2012, 2013, and 2015 in debug mode. And if you look at these graphs, you can always find this big graph with like a lot of content, which is somewhere central, and that's the actual function that he compiled. So there's really just one function that collects data about the system and prints it out on the command line. And that's the thing that I would be interested in if I would want to analyze malware, like the biggest nodes with the most connections that contains the most information. Interestingly, the other nodes you can see there are actually compiler generated and do not really add information to the analysis process. And that's the whole point of the project. I think in the future about reducing the graphs that I produced to only show the nodes or the items within the graph that I consider holding the most information. All right. This much about the graphs. Where's the actual stuff? So, as you've seen, what I tried to produce were graph visualizations, but you might understand that this is not always the right way to go. Like there's complex binaries, there's big binaries, and they create ugly graphs. So there needed to be different ways to gather information about the actual binary that is human readable and understandable. So I started thinking about extracting behavior indicators from binaries, which for me, I worked before in antivirus, and extracting indicators from binaries sounds like magic stuff that doesn't work on half of the binaries. But I'll explain more about that in a bit. What I also tried was extracting metrics. As said before, I do not want to do machine learning, I do not want to get indicators, but I wanted numeric values that I could easily store that would help me evaluate the binary in front of me. There's a couple of indicators that you can extract from the graphs that I created. And I will show you how these are useful to, for example, find packers or find dynamic API loading or find binaries that are too abnormal to be good. And in the end, I will be talking about a bit the graph database that I mentioned before. So again, let's get back to the malware or to the graph that I talked about before. Its name is Win32 RedZip, or actually I don't really know what its name is, but that's what Microsoft calls it. It's a piece of targeted malware. It comes unpacked, and the strings are all in clear text. It does not do dynamic API loading. And the binary itself I grabbed from a repository of targeted malware. This repository is hosted by Citizen Lab. They created actually a list of file indicators, which contains a long list of file hashes, which all refer to binaries that they found within targeted attacks. This is a fairly interesting repository, as you have the guarantee that all of the binaries are targeted or have been used in a targeted context. About the dataset itself, what I found out is that a lot of the binaries in there are rather small, and a lot of them have the intention to download second-stage malware, which is fairly common in APT contexts, and it doesn't actually help in analysis to find out that your binary is actually not the thing that you wanted to see. But still, for my purpose, they were perfect because they were rather small. And it might also not surprise you that this approach that I went has a problem with fairly large binaries. So binaries that are bigger than 500 or let's say binaries that are bigger than 900 kilobytes, or binaries that are highly interconnected, like that have very complex graph structures, take a long time to parse with the approach I currently have. But I do also have the plan to make the code more performant and to fix things, and then, at some point in the future, it will be a really useful tool. Anyway, let's look a bit closer at the graph. So, again, not sure you can read that. I might be able to help you. This is I tagged it callback. It's actually a thread handler function, which, if you look at the graph, is the big orange node or the big green node on the left side. This is one of the handler functions, which, as you can see, contains a lot of CNC commands. You, for example, have cmd enum directory and cmd file upload and cmd file delete, and so on and so forth. So this is probably the parsing function of CNC commands. One could consider that before that, the binary was communicating to the CNC server and receiving commands, and this is the function to parse the commands. What else we can see in there is this function. It's one of the functionality nodes, which collects information about the infected machine, like, for example, the computer name, the installed operating system version, the drive type, the free disk space, the description for the local central processor. Like, you can see a lot of information that refers to the machine that was infected. This is also one of the graphs, the big graph on the right side, on the right bottom side, which looks like an egg. So these two nodes are just an example as for what one could see within these bigger graphs. I have some more, like, for example, one feature that aims to download the system. So the process tries to retrieve the shutdown privilege and then exit Windows. We have one function that tries to write to a log file. The log file is located at C and it's called log.log, like very, very stealthy. And we have one node that shows a domain that is properly used for communication to the C2 server. Like, you see there's a lot of nodes that actually contain a lot of information actually that help understanding the binary, but this is not really what I created the graph for. Here's another example which shows a bit better of what I intended to do. If you can maybe read that. Here is an API, it's called NextHook. What the picture doesn't contain, further up, there's a set Windows hook function, which installs a hook on the system and potentially installs a global hook, which is able to control all the processes that are running on the current desktop. And with this, it might try to lock keystrokes. You can see they get key state API, and you can see more of it. So these functions that are visibly connected are probably part of a keylogger component that is hidden within the binary and tries to steal keylogs from the applications that the user runs. I'm not sure if you can read that. There's other API somewhere in that graph which retrieve the name of the desktop window that is in the focus. So probably this name is used for structuring the keylog file where the keylogs are being stored. Here's another example of a graph which doesn't do a lot but tries to find installed antivirus software on the machine. So you can, for example, see a reference to the string ISA, the reference to Kaspersky Lab, and right in the bottom you find a reference to GData. I was very happy to find that. And one would consider that this function, the big egg in the left bottom of the graph, is used for a function that tries to detect security software on the machine. So these are things that a human analyst can gather from these graphs by looking at it and paying close attention to APIs and strings that are being called, and by putting them in context himself. One thing that I'm not able to do with these graphs is actually reconstruct the structure of the function. So I did not consider basic blocks, and I did not consider the actual content of the function itself or the order in which the APIs are supposed to be called. This I left out because it would be a lot of data to gather and a lot bigger graphs to create, which would deny me the possibility of visualization. In practice, I found it very useful to have the APIs just listed and use my personal knowledge to gain behaviors from the lists that I found within these nodes. In another approach later, I tried to automate exactly this to help in behavior extraction. But here's another graph which does not show all that much information, which is to visualize another application that the tool could be used for to find binaries that look suspicious or look runtime packed. This binary, for example, contains APIs to download content from a remote server and to execute a binary, which, although the graph doesn't show any connection between, the human analyst could deduce that this is another which also tries to download and execute the binary. But as mentioned, These graphs potentially provide a holistic view of the binary content, but they still need a human to actually understand what is being shown within the graph. And also they are not always feasible, because if you put like a serious application into this graph algorithm with dedicated software developers who knew how to structure code, you get graphs like this. You probably can't see much there. There's a lot of nodes in there. You can still scroll in there and see what data the nodes contain. But a human analyst has very big difficulties in finding the connections between the nodes and see how they're interconnected. So in the first approach, I tried with text. It's possible with the tool to output the entire graph as text and then just go searching through the text. But this is also not very useful in terms of edges, so you still can see a connection between the nodes and see how the functionality is distributed throughout the nodes. So I came up with a different idea, actually the rogue behavior detection. So what I tried to do is use the graph and the data that is contained within the nodes to gather information about the behavior. Therefore, I defined a set of API call gadgets, which for me as a human analyst would be functionality that I would expect within malware or within these targeted binaries that I was looking at. And then I tried to do pattern matching of APIs. Again, I come from an antivirus world, and their pattern matching is like what they did for 20, 30 years, and we're supposed to be really, really good at that. So what I did was iterate through the data contained within the nodes and search for API patterns, and therefore I actually had to mingle the API names a bit to just contain the most important part of the API name. And from there, I would search for the first API call within my call patterns to find what I call anchor nodes, like primary nodes from where I start searching for the remaining patterns to see whether in this area around that specific node I could find my functionality that I was searching for. Of course, again, there are problems. As mentioned before, we have indirect function calls, which with this approach I cannot find. And also I figured out if I use bigger call gadgets, which might find specific functionality very well, how it is implemented in one binary, I learned that malware authors, just like any other human, have different ways of implementing things. This was a big problem, as I found, for example, to find a pattern for iterating the file system, where you have like find first file, find next file, and in the end you would have a find close to close the handle, right? But actually, you wouldn't think like a lot of malware authors do not close their handles. So I found out that I would rather have to keep my gadgets as small as possible, which comes with different issues again, but you will see in a bit. And in the end, of course, this approach still needs someone to interpret. So far, I do not have an algorithm to automatically draw conclusions, which is also something I do not want, because as mentioned in the beginning, I just want a tool to help analysis. This is not a 100% automation approach. This would be the call gadgets. Again, I don't think you can read that very well. This is basically lists of API calls that I consider functionality. That, for example, we have a pattern that's called write file. So someone would have to create a file and write the file. We have rec query, which means someone would have to open a key and query the value. We have create remote thread, which means create thread, write process memory, read process memory, etc., resume thread. These are like gadgets that I saw in the past and I considered useful. And this would be one example output. In this output, there are the specific functionalities and the referring nodes being saved, in which I found these patterns. As you can see, the list is still very long. And from before, the functionality itself doesn't really say anything. So from this output, I cannot deduct that a log file was being created and it was being written into that log file, and that log file was being sent to the remote server. This is information I cannot gain from this output, but I would need to have a look at the graph or at the binary itself. This information only helps in a quick analysis of which kind of functionality could be hidden in a binary, and the analyst still has to draw his own conclusion about what he thinks is hidden behind there. Also, this output does not help in determining whether an application was benign or malicious. It just shows indicators. Here is two more examples. The first one I consider rather complete. It's a dropper file I found within my sample set, where, for example, you can see that the registry key is being modified. There's two nodes which potentially create processes. And then there's the functionality to write a specific file and to execute a file. This is indeed a dropper, and from that functionality I see listed there, I could conclude that this malicious binary actually tries to execute a binary. And then the bottom you see also an interesting output. This was a rather big binary. This was a binary of about 300 kilobytes, where you would expect some functionality in there. The graph of that binary also showed that there's a lot of functions, so there should be something happening. And the only APIs I could find was load library and get proc address, which is a clear indicator that APIs are being loaded dynamically. On the other hand, of course, you have packed and obfuscated binaries, which do not show a clear graph. This is one of the examples, and also I have a lot more examples, which usually are vertical or horizontal lines of functions, where either no references could be found or actually no references are being present. And this is my favorite binary. This was actually not a 2 kilobyte binary, but a rather quite big binary where only one function was found. But then again, as mentioned in targeted binaries, there's very little runtime packers being used, but usually these binaries try to hide something. So the simpler versions, for example, that dropper you saw before, they show about everything, all of the functionality that they contained. But a lot of binaries, like that graph you can see on top, try to hide parts or all of their APIs and their strings from the human analyst. So therefore, I wanted to find metrics which help me evaluate these graphs and whether there's something being hidden within that graphs. That's why I came up with a bunch of metrics. You actually wouldn't believe how easy it is to extract metrics from graphs. There's so many numbers and so many possibilities to describe graphs. But my goal was to find useful metrics that help me describe the amount of information that was contained within my nodes and the amount of information that was contained within the graph structure. Now, why would I need metrics? Measuring things is fun. I'm having a very good time in measuring my binaries. And actually, so far, analysts do not have a standardized metric or a standardized way of measuring sophistication. A lot of binaries are being said to be sophisticated. For me, calling something sophisticated means just that the person who analyzed it doesn't really understand what it's about. That's our modern sophistication. Also, there's very little metrics for actual complexity of binaries. There's big binaries, there's small binaries, there's complex graphs, there's less complex graphs, but there is no measurement to say how difficult it actually is to analyze a binary. This is a problem if you, like certain companies, actually try to sell analysis services, because you can measure that in hours, but you cannot at one glance say, oh my God, we're going to need 1 week, we're going to need 2 days, we're going to need a month to analyze a specific set of binaries. Also, a problem that we have, IOCs sucks. I might have mentioned it before. And again, there's little measurements or little possibility to measure binary attributes. So again, I went back to my preferred RedRE binary. Here is some random information that the tool spits out, which can be used for identification. If someone thinks about putting the data into a database, for example, I did not do that. But the more interesting things are measurements that you can grab from the graph structure itself. Here, for example, are the statistics that I gather during the graph parsing process. So it's, for example, interesting how many nodes are contained within a binary as compared to how many edges are there. Are there a large number of nodes and very little number of edges? Or are there, for example, very little APIs actually being referenced within functions? Are there a lot of calls that refer to locations outside of the code section? Or are there a lot of strings that are actually having references to code but are not referenced within a certain function? This is information that helps you evaluate the binary you're looking at. It would, for example, be weird if this big binary, which has 70 kilobytes, does only have a very small set of APIs being referenced within functions. So this way, these numbers help evaluate how much information is contained within the nodes of the actual functions, and whether the binary might try to hide, for example, APIs or strings. Also, the numbers help comparing. I did not do try to compare binaries, but they could be useful in seeing how, for example, different versions of one specific Trojan compare to each other, whether functionality was added, whether a different optimization step in the compiler, a different optimization option in the compiler was used, whether the authors changed anything on the binary that was significant, or whether some numbers changed, so that this could be an indicator for improvement on the actual binary. Then I got a metric which I call FatNo Detection, and at some point I also call it spaghetti code metric, because it helps me find the major nodes within the graph that are very well interconnected within the graph structure and contain a lot of APIs and strings. This is usually the case if you have like one central node which performs most of the functionality of the binary. Then you find this spaghetti code when you have like these big monsters. These are usually the ones I consider interesting, and then occasionally there are some that I consider awkward. What I found out during this project, what actually makes sense, is that there's usually some kind of equality between the number of strings and the number of APIs that are being referenced, because one would think that strings in binaries are actually being used by APIs or by functions that process them. So as you can see on this list, the numbers usually are in equal ranges. You have 23 and 29, you have 3 and 3, you have 6 and 6, you have 1 and 1. So this for me indicates that APIs are using strings. But if you have like one node that contains a lot of string references and not a single API, something's weird there. Usually that identifies nodes where the string parsing went wrong. Then you can look for the reason why the string parsing went wrong. Maybe there's obfuscated strings, or maybe there's obfuscated code that was wrongly identified as strings. This is certainly interesting indicators. Also, of course, I use more math on the graphs, like mathematicians love graphs. I do not love math and mathematicians, but the numbers are actually useful in certain contexts that the NetworkX tool spits out. For example, we had the average node connectivity per degree, which is interesting to see how many different degrees are contained within the graphs. Like how many different numbers of outgoing or incoming connections the different graphs have, and how well they're connected on average. This usually is useful to see whether the list is longer and the numbers are higher or the numbers are lower, because packed binaries usually do not show high interconnectivity. Packed binaries usually have very low Ks, very low degrees, and these are badly interconnected. So this way you can find out whether the structure is abnormal as compared to normal binaries. Also, I created a histogram of the out degree centrality. I'm not sure if you can see that down there. Like the second line of numbers, that's my histogram. That's how the out degrees of the specific nodes are distributed. Out degrees are, for example, if one function calls another, that's considered an outgoing node, an outgoing edge within the graph. And it's interesting of which nodes call the most subfunctions. This histogram usually is distributed somewhere in the middle. There's always some nodes that do not have any connections, that are code that is not connected within the graph. That's the number on the very left. There is, usually, that's the next metric actually, there's always about between 20 and 50% of the graph that is disconnected. With C++, it's usually higher because I'm not able to manage member functions with other nodes in the graph. But with usual C binaries, that's about 20% of nodes that are unconnected. If this number is really high, like if you have 70, 80, or 90% of your graph that is being disconnected, something is wrong. And this histogram in the bottom helps evaluating this. Like if the histogram shifts more to the left, you have a highly connected graph with a high number of disconnected nodes. If it shifts to the right, you have a highly connected graph without a high number of disconnected nodes. These numbers help evaluate the graph with the help of numbers. Also, I found it interesting to search for the average number of APIs per kilobyte and the average number of strings per kilobyte. This is a metric that helps finding out whether strings or APIs are being hidden from the parser. And of course, there's more metrics that I plan to implement and a lot more numbers that I plan to create, because there is a lot more information that's actually being contained within the graphs, like the use of specific libraries, the variants of APIs that are being used. Like for example, there's runtime packers which try to look like normal applications, and they will just show random APIs. I've seen it a lot in the past. One, I think it was called Bfrost. One malware did that a lot and showed a lot of APIs. Now, if you run a usual static analyzer through the binary, it will find a lot of, I don't know, functionality, which in fact is, in my opinion, highly variant, because they usually don't consider the APIs to be in context, but just put random APIs in there. With the variance of APIs being used, I would guess one could detect it. And of course, data cross-references are also an interesting metric to add to the graph structures. Now finally, I'm almost done. I used Neo4j as a backend to persist the graphs that I created. What I still have to do is find out whether this graph database can help me in finding connections or correlations between binaries themselves when they're stored there. And a little less useful, actually, Neo4j also outputs visualization, as if I didn't have enough visualization yet. What is interesting, in Neo4j, you can, well, in any graph database, you can store any kind of attribute of a binary as a specific node. And then you can, of course, again, store references to that node. So I went away to store my strings and APIs as dedicated nodes in there, and not only the functions themselves. So later on, I can extract binaries which reference the same APIs and evaluate how many APIs and strings they share and whether there's indicators that binaries have in common in an automated way, which is nice. All right, I'm actually almost finished. What do I plan to do now? As I said, the tool is still in the process. It's a proof of concept. It barely ever crashes, I promise. I did a lot of checking. It doesn't work so well yet with C++. As mentioned before, I'm having trouble matching the member functions with the actual locations where they're being called, and Delphi is a big issue. How many people in the room are actually reverse engineering malware? Some? How many people in the room to do that do not hate Delphi? From here? Anyone? No? Okay, so Delphi is an issue for all of us. And cases that I haven't tested yet is anything that goes outside of Win32C binary. So with 64-bit, it should work. The tool works. I'm not sure if the data is accurate. And the same works for drivers. Okay, this was actually it from my side. I thank you very much for your attention. And if you have any questions, I'm here to answer. Thank you. Please. I can throw it if you want.
Don't worry. Yeah, thank you. So, about the pickers detection, do you have some, you know, we have a lot of kind of pickers, Temida, UPX, a lot of pickers. But you're talking about some generic ways to see if the binaries are actually picked. You know, my question is, the tricks you show to us is to sum any kind of pickers or some specific pickers detections, you know?
Yes, so there's still a lot of directions one could go. I thought about that actually, that I think this works, that you could see a difference between packers as well. But as you saw, the graphs didn't really contain a lot of information. Of course, you could try use these features to differ between different packers, but as they contain very little features, that might be difficult. But the graphs have so many, or the whole tool spits out so much information, so one would have to evaluate whether you could really see differences between them. I might really throw the microphone someone.
We use this because
okay. All right, I'll stick with that one. Any other questions?
Hi. How did you deal with all the garbage involved in getting only the stuff that you really wanted for the nodes? I imagine you got a lot of garbage between the code?
Not really.
It was not really.
So I want the minimalistic approach. I mean, RedRE is fairly, is pretty great in just spitting out exactly the data that you want. So it would give me a list of functions, it would give me a list of string cross-references, it would give me a list of function cross-references, it would give me a list of symbol cross-references. And with these lists, it was really easy to just put the graphs together. I mean, there went a lot of time into bug fixing and into bug fixing of RedRE and into parsing the data that RedRE puts out. But in theory, like, it's all super simplistic. I could imagine that there's a lot of problems coming up if I try to add more information about the actual binary structure and about callbacks and C++ and whatnot. But that hasn't been a problem so far. Back there.
Hi. Do you keep any kind of control flow graph information in your graphs? Like, for example, you showed the different nodes. It would be very useful if you had like the order in which they were executed. When you try to get a high-level view of what the binary does, right? You have all these nodes with different functionality with APIs and strings, but do you keep the order in which they're visited by the execution flow?
To find out the execution flow, there will be a lot more work to be put in there.
But even statically, you do have some indication of how this goes, right? Because you have the entry point of the
Could you
binary.
put the microphone to?
Yeah. So.
Thank you.
But even statically, you still have a lot of information there because you have the entry point of the binary, and you can walk through the different nodes, right? I mean, you have to keep the order as you go through the control flow graph and create your nodes with the strings and the APIs. But this information is there. So, because we're doing something, so we basically do reverse engineering for auditing, and we don't do exactly that, but we do something similar in order to give us like a very high-level view of like a file parser or something like that. So. Having the order in which the different nodes are visited, it's very helpful in like getting like a high-level overview of the parser. So I think it would help you as well with that analysis if you were keeping the order in which the nodes are visited.
Yeah. So in my dream world, this is actually not a standalone tool, but I would love to see this integrated with the sandbox, for example, in the future. So I could think. I mean, there have been approaches about multi-path execution within sandboxes, I know that. But I could think that the static analysis component within a sandbox would actually be the most productive solution to work with. I know that here I'm lacking a lot of information that a sandbox can get, but I'm having a lot of visibility that the sandbox can never have. So I would believe that putting these two approaches together would finally make a near to complete picture of the binary. But that's like far in the future from now. Well, thank you. Also, thank you for the questions.